All right, day 16. What do we got? We have cat faces. Hmm. Okay. Did not actually understand that. I see. Okay, so the annoying part here is just reading this in. Okay. Oh, Uh, right. Coins. Huh. It's a big number. Uh, It goes to 7, 10 goes to 15, 100 goes to 138. Okay, so I think this is right. Eight zero zero 1466814. Nice. A second level lever. Uh, okay. Oh, let's see. I see. Eight. Nice. Okay, so what was going on today? Uh, so we're given um, basically these three or whatever, some number of columns of strings, uh, and also these indices. And so I don't know, in one turn, you walk like one step through the first column, two steps through the second column, three steps through the third column. Part one is just in 100 turns. If you do that, um, how, I don't know, where are you in each column? Uh, so pretty straightforward. I was a little slower on this part relative to other people. I guess because I don't know, I probably, like, you could do a faster thing. I like sort of did, uh, I don't know, fancier parsing maybe than I would imagine some people did. Anyway, in part two, sort of the same setup, except you want to pull it a lot of times. What is this? Like a 2 trillion times, basically. And then you want to compute this scoring function, which is like based on which symbols appear. So obviously we can't do we can't actually pull the lever 2 trillion times, but what we can do is keep track of cycles. Um, so keep track of where we are in each column. And uh, if we see that same like position again, then we know that we're in a cycle, right? So like if it takes us, 27 spins to get back to the same position, then we can keep track of how much our score increased from the last 27 spins, and then we can say, okay, let me do like a trillion, or I don't know, a billion times 27 spins, and I know that that will not change my state, but it will advance time by 27 billion, and it will advance my score by, you know, 20, by a billion times whatever, however much score I got in the last 27 steps. Um, so we can just walk through, we're going to hit some cycle at some point, and then we can walk through a bunch, so skip past a bunch of time. You can sort of see the jump in my output, and then I guess it takes a while, some thousands of, maybe tens of thousands of spins to get to the cycle. But eventually we get to a cycle, we get to jump forward about 2 trillion spins, and then we also, do the remainder. So that's a nice way of doing that. Okay, I'm not going to bother to jump to it, but at some point it jumps to it. So that was part B, and then part C had a different challenge, which is that the path sort of diverges. So you want to know how many points you can get in 256 spins, but before each spin, you can either leave it alone, or advance all the columns by 1, or like up all the columns by 1. So if you do this naively, you get 3 to the 256 operations, which is too much, but we can use dynamic programming, where we keep track of how many spins we have left and what the state is. And, there's only so many possible states. So what's the point? We can write a recursive function to solve it. Given that I have this many spins left, I'm in this state, what is the min or max that I can get? So that's relatively straightforward, right? You try all 3 possible options of like up, stay still, or down. And then you say, okay, what would be the new state if I did that? What's the score of this spin? And then I can do, recursively compute what's the best score or worst score I can get from there. And figure out which of these 3 options gives us the best score. But I guess the key point is there's only so many arguments that you can call this function with. So if we memorize the function, then we're only going to evaluate it, I don't know, not that many times. Let's see. How many times do we actually end up evaluating it? Okay, only 131,000 times. It's amazing that it takes so long to do this. I guess I wrote it in kind of a slow way. I don't know. This scoring function could probably be optimized. But anyway, it only ends up evaluating 131,000 possible states, which is a lot less than 3 to the 256. So it runs in a reasonable amount of time. And that's it for part C. So both part B and C were pretty tricky today, algorithmically, I would say. So I'll be interested to see how people do on them. See you tomorrow.